here you can see the Tensile testing machine that has upper jaw, lower jaw, which are connected to cross heads. And this is the frame, so loading frame that holds everything together. So there is also a hydraulic component inside of this big lower part that allows for increasing the pressure of the pumping liquid and subsequently transmit some force to these jaws. And on the screen to the right, you can see that there is a software associated with that machine that is named Instron. And this software is used to control this machine. So as you can see here, there are some displacements that can be recorded, and they're indicative of some deformation. And there are also some forces being recorded as the measure of the pump fluid pressure. And also, we can see that strain can be calculated online on the spot during the test. And so this is the basic setup. We use these controls to adjust the distances and place correctly the sample within the jaws. And here also the full stop in case of any emergency, so we can stop the machine and maybe just prevent some injuries, because it is quite powerful tool that is capable of, let me see here, it is 300 kilonewtons, so 300,000 newtons of force can be handled with this machine. And it can easily probably injure someone if handled inappropriately. So the next piece here, important, is the strain gauge, or in other words, the device that is used to record the curve more exactly or more accurately. So this, as you can see, has some springs, so upper and lower spring, that are attached to levers, upper and lower. And within this box inside, there is a strain gauge that reacts to the deformation supplied, or basically due to movements of these levers. Once the sample is deformed, so this motion is transmitted here, and the strain gauge reacts on that displacement by generating some signal in this box. And this signal travels through this cord and down to the computer, so we can record the tensile curve. So this strain gauge is used to mainly record the first portion of the curve, which is related to straight line where material is deformed elastically, and this portion is used to determine modulus of elasticity, and the strain gauge is used to make this as accurately as possible. Yes, we can run the test without the strain gauge, but the accuracy of determining of the modulus of elasticity will be much lower and will not represent the true reality. So let's maybe go back here to these jaws and jaw plates. So currently there are installed plates to handle samples of some rectangular cross sections, and to run our samples of round cross section. So this is our specimen for today. So we will need to replace these jaws, not jaws, but jaw plates. And this is the jaw plate that we would like to install. And there are 4 of them, 2 at the upper jaw and 2 at the lower jaw. So this one, for example, will come as pair, like positioned like this, and I'm going to show you it this way so you can better understand the geometry of these jaws. So as you can see, there is some slot machined, so we can insert our sample this way. So it is located in this between these plates and is locked once we adjust or do some pre-test adjustments. So as you can imagine that the second plate will come just in front of you, locking it, locking the specimen between the jaw plates. And you may notice that there is a little bump machined, so this will actually transmit the tensile force, biaxial tensile force to the sample. So again, you see, once it slides like this, boom, it bumps, and this little bump will transmit the force we want to supply to the sample. Okay, so now let's change the jaw plates. And the jaw plates are holding there, fixed in the place with the springs. So the spring looks like this. It is just somewhat stiff spring that would allow these jaws to be fixed on place using these handles. So it's quite simple device, but yet really genius. So I'm going to remove this, and I'm going to open the jaw more and slide it off. Okay, so this is the jaw plate that you see this flat, and there is some texture to the surface, so flat specimens can be properly fixed. So like this. Okay, let's remove it and remove the other one. And we're going to place here the ones that we're interested in. Plates should be facing the same way. So I'm all place them to the right. So I can slide the sample with no problem. Let me show you the result. So again, this is our upper jaw and jaw plates fixed with the spring. And here the lower jaw, also with 2 jaw plates fixed with some springs. Okay, so now, once we've done this, and looks like we have a sample to test, so I think we can try. And before we start any test, we need to make sure that our tools are available to us, which we will use to control some of the parameters. And I will explain in a second what it is. So it is a caliper. So we use these to measure the diameter of the sample right before the test. And we will use this diameter, or software will use this to generate the curve properly according to the equations that we were talking about. So you remember stress is equal to some force being generated by this machine divided by original cross-sectional area. So original means before any loading. So we also use this punching device to produce some marks using these two really sharp pins. So by placing the sample here, so we will punch some marks, and I'll explain why in a second. But let's maybe spend some time with the sample itself. So our sample is a round bar, and this round bar comes from some process which was used to create this bar. So first it was machined, and maybe it is rusty now because of some heat treatment procedures. This is steel 1040 annealed. So therefore, the annealing process that took place at some high temperature brought this sample to high temperature. It was held there for some time, and it was cooled after. So with these high temperatures, what can be associated is the reaction of oxygen from the atmosphere in the furnace with the metal itself. So in this case, it is steel. So iron was reacting with oxygen and got oxidized. So before we do anything and measure, to make sure that our geometry is accurately measured, so we would like to remove some of this oxide scale. So as you can see, it goes off and flakes off. So maybe it's not the best plate that I choose to clean the sample, but it was just something that I was laying around, and let me check if I can find something better in the shop. So looks like I can go with maybe something else, maybe this wrench. So that would be better. Hope so. So therefore, all I'm trying to do now is to remove the oxide scale. This oxide is fairly brittle, and if we leave it, so it will compromise the measurement of the diameter, and also may hinder the punch marks that we want to place somewhere here in the middle. And therefore, so it looks like it's almost good. Maybe not best, but let's not spend much time on that. So next, I would like to show you that the shape of the specimen is like this. So there is some portion right in the middle that is machined to lower diameter. So we would expect any deformation of the sample happening between my fingers here. So sample will be deformed over here preferentially, because here we have lower diameter, and this should concentrate all the load and stress in this region. So why we need that? Because we want to control the breakage or let's say failure of the material, and we want to have this failure occurring around here. So that would be ideal. And so we can place our strain gauges somehow here with these springs. I will show you how. And this also ensures that the strain gauge is not, well, will not break. So will survive the test. So you can imagine if the sample will break here, for example, what would happen with this part? It may move really quickly and just stretch the strain gauge to the point of unusability. So, okay, let's now go to caliper. So caliper is something that we will use to measure the diameter. And this particular type is equipped with electronic device here that is used to provide the direct measurement using this display. So after I started, so I can select either inches or millimeters. So we'll be working with inches because Tensile machine is set to work with inches, and so I just don't want to change this. And there is a little 0 button, so you may notice that once I'm turning it on, so you see the measurement is weird. It is just really quite off. And what I would like to do is to 0 it. So now, once I'm moving these lips apart, so I will be able to measure things, you see? So it changes from 0 to some value and back. So definitely this is really delicate and sensitive device, and since it measures with high precision, and we don't want to drop it. So be careful every time you handle something like this, because if you drop one of those, it becomes garbage. So now let's measure the diameter. So again, I see here some, oh, that's good. So make sure that you press it, I would say, gentle enough to close any gaps between the stuff that you're measuring and these lips of the, or tongues of the caliper. So now what I'm doing, you see, I'm sliding it in and I'm closing this gap, right? You see, I'm closing the gap, and I'm making sure that my part is situated perpendicular to the caliper. And so my measurement now is this. So it's 0.4910 inches. So I'm going to write it down, 0.497. .75 inches. So again, and if you use caliper that is not equipped with this device, so I will show you later how to do that. There are different calipers with different precision, and so you just need to be careful the way you read it. Okay, so now what we're gonna do is we're going to use this device to punch some marks, and it's pretty simple. So we just need to position it exactly in the middle, position the sample exactly in the middle of the punching device, and we just need to smack it so we are able to produce the mark. So okay, now that was pretty easy, and why I'm saying so is that you can see the marks. So one and the other one, I hope you guys can see it. So these marks are used to see how long the sample will become after its failure. So this will be used to calculate some ductility. Elongation is the measure of ductility, and as well as the diameter. After the test, it will change. So we will be able to see this change by using this sample holder or specimen holder, just placing it back and aligning everything and measuring. So that's going to be our very last step. And now let's move the sample to the machine.